Hey guys, welcome to Safi Mixed. In this video, I want to find the mean or the average of Poisson distribution. We know the relation for Poisson distribution is given by P of n equals n average to the power n divided by n factorial exponent minus n average. Since here n is the random variable and n bar is the average of binomial distribution. If you recall from our video on Poisson distribution, whose link I'll add to the description of this video, we were proving this relation. We use n bar as the mean or average of binomial distribution, and we want to prove here that this average of the binomial distribution is in fact also the average of Poisson distribution. So to do that, we know that in every distribution, the average of a random variable, I just want to write a general definition. The average of a random variable in any distribution is obtained by summing over all the possible value of x and the random variable times p of x. This is the general definition where x, the limits are from 0 to infinity. This is the general definition for finding the average of a random variable in a distribution px. And if I apply this definition to Poisson distribution, that means I can replace the x with n. So I would write n average would then be equal to summation from n equal to 0 to infinity n times p of n. And if I use the value of p of n from, let me call this equation 1, from equation 1, this equation becomes n equals 0 to infinity n multiplied with n bar to the power n divided by n factorial exponent of minus n bar. Now, the exponent is obviously independent of the summation parameter, therefore I can take that to the left of this summation and want to rewrite this relation in the form exponent minus n bar sum over n equals 0 to infinity n times n bar to the power n divided by n factorial. Now look, for n is equal to 0, this term is 0 because 0 times anything is 0. Therefore, I rewrite this equation. I remove the 0 term from the summation because that goes to 0. That has no contribution to the whole summation. So I write this as minus n bar sum over n equals 1 to infinity n times n bar n, and I reparameterize the denominator into n minus 1 factorial. That is, n factorial is in fact a factor of n times n minus 1 factorial. And in doing that, I can cancel this n with this n. And similarly, what I do, at the same time, I subtract minus 1 from the power of n bar and add plus 1 to the power of n bar. So I can do some other parameterization, and I want to do that over here. That means at this side, I can write n bar equals, from here, I want to write this thing, exponent minus n bar sum over n equals 1 to infinity, and this would become n bar power n minus 1 times n bar divided by n minus 1 factorial, right? Because this thing is equal to n bar power n minus 1 times n bar, so I'm writing that over there, and I'm taking this n bar to the left of the summation to write it like this, n bar exponent minus n bar sum over n is equal to 1 and n bar par n minus, and then divided by n minus 1 factorial. And now I want to reparameterize this random variable by defining m equals n minus 1. And we see when n is equal to 1, this implies that m goes to 0. And when n is equal to infinity, again n is equal to infinity. So if I want to substitute this value for n minus 1 at these two positions, that means the sum would go from n is equal to 0 to infinity. I missed the infinity over there as well. So that means I can rewrite n bar equals n bar e minus n bar sum over m equals 0 to infinity n bar to the power m divided by m factorial. And again, this thing, if we look carefully, is the Taylor expansion of exponent n bar. So I can write this equals n bar exponent minus n bar times exponent plus n bar. I can write it like this. There is no minus. So I can put these two exponents into a single exponent in the form exponent minus n bar plus n bar, and obviously minus n bar plus n bar is 0, which gives me like n bar into exponent power 0 equals n bar. So this is very interesting. This initially we used this as the mean of binomial distribution, and now by defining this procedure, that is, we want to find the mean of Poisson distribution, and it happens that the mean of Poisson distribution is exactly equal to the mean of binomial distribution. So the mean of Poisson distribution and binomial distribution coincides exactly with each other. Thanks for watching.